Now we turn to another field, Galois field 2, which has just two elements, 0 and 1. It's named after Galois, who was a remarkable mathematician who laid the foundation for group theory, but died in a duel at the age of 21. Addition of 0 and 1 in the Galois field 2 is just like exclusive OR. That is, adding 1 and 1 gives you 0. Multiplication is just like ordinary multiplication of 0 and 1. And the usual algebraic laws hold. For example, multiplication distributes over addition. And we'll provide a simple module called GF2 that defines a value 1. This value acts like the 1 in GF2. And we'll use 1 when we write programs that operate on GF2 values. Here's an application of GF2 to cryptography. Now suppose Alice wants to communicate with Bob. She only wants to communicate 1 bit, let's say. It's called P, the plain text. So they use a crypto system to ensure privacy. Now here's the table describing the crypto system. Alice and Bob agree beforehand on a secret key, K. And Alice will encrypt her plain text P by using this table to figure out the ciphertext C that she should transmit to Bob. By studying that encryption table, you might notice that it's really just the addition table for GF2. We can therefore implement encryption like this. And here's how we would use it. Import the 1 from GF2. Let's say the key is 1 and the plain text is 1. We compute the ciphertext using encryption, and that's what we get. Now once Bob receives that ciphertext, can he figure out what the plain text is? Well, he knows K, the key. He receives 0 and 1 as the ciphertext. Now, for any particular value of K and any particular value of C, there's only one value of plain text that's consistent with those. So Bob can determine what plain text was intended by Alex. Now suppose an eavesdropper, Eve, observes the value of C. She doesn't know the secret key. Can she learn anything about the plain text? And here's the simple answer, no, and here's why. Suppose that the ciphertext is 0. Remember, Eve doesn't know the key. She can look at this table and say, oh, the ciphertext is 0, so maybe the plain text is 0. That's the case if the key is 0. Or maybe the plain text is 1 if the key is 1. Since she doesn't know whether the key is 0 or 1, she can't figure out whether the plain text is 0 or 1. And here's a somewhat more sophisticated answer. It depends on how the secret key is chosen. So let's suppose the secret key is chosen by flipping a coin. So the probability is 1/2 that the key is 0 and 1/2 that the key is 1. Let's look at it from Eve's perspective. Before she even goes out to eavesdrop, she reasons as follows. Suppose the plain text turns out to be 0. Well, the key is chosen randomly. So looking at the first 2 rows of the table, the probability that the corresponding ciphertext is 0 is 1/2, and the probability that the ciphertext is 1 is 1/2. Now suppose that the plain text was actually 1. Looking at the last 2 rows of the table, the key is chosen randomly. So the probability that the ciphertext is 1 is 1/2, and the probability that the ciphertext is 0 is 1/2. So the choice of the value P, the plain text, is not reflected in the probability distribution of the ciphertext. Eve doesn't learn anything from observing C. She might as well just stay home and flip a coin, because the ciphertext is just 0 with probability 1/2, and 1 with probability 1/2. What is it about this crypto system that leads to perfect secrecy? Why does Eve learn nothing from eavesdropping? Well, let's define the function f0 as follows. f0 takes as input the key, k, and outputs the encryption of the plaintext 0 with that key. So according to the first two rows of this table, f0 of 0 equals 0, and f0 of 1 equals 1. This function is one-to-one and onto. Now, when the key k is chosen randomly according to the uniform distribution, that is, when k is 0 with probability 1/2 and 1 with probability 1/2, then the probability distribution of the output is also uniform. That is, the probability that the ciphertext is 0 is 1/2, and the probability that the ciphertext is 1 is also 1/2. Now let's turn to the function f1. f1 is the encryption of the plaintext 1 with the key k. Now, according to the last two rows of this table, f1 of 0 equals 1, and f1 of 1 equals 0. So this function is also one-to-one and onto. And so when the key is chosen uniformly at random, the probability distribution of the output is also uniform. That is, the probability that the ciphertext is 1 is 1/2, and the probability that the ciphertext is 0 is also 1/2. So it seems, regardless of what the plaintext is, the probability distribution of the ciphertext is uniform. 1/2 probability of 0 and 1/2 probability of 1. So the probability distribution of the ciphertext doesn't depend on the plaintext when the key is chosen randomly. From Eve's perspective, there's no point in observing the ciphertext. She knows it's just going to be a bit, either 0 or 1, chosen according to the uniform distribution. She might as well stay home and flip a coin. This is the idea for the crypto system called the one-time pad. If each bit is encrypted according to this table with its own one-bit key, this crypto system is unbreakable. No eavesdropper can learn anything. Now, in the 1940s, the Soviets seemed to have run out of key, and they started reusing bits that they had used from previous messages. And this was discovered by the U.S. Army's Signal Intelligence Service. They started slowly finding places where they could decrypt little bits of the message. This led to some very important intelligence, including information about the Soviet espionage on nuclear weapons. And we only learned about this in 1995 when information on this project, the Venona project, was declassified. Here's another application of GF2. Imagine you need to stream video through a network, starting at this point. Now, if there's only one recipient of the video stream, since there are two paths that share no edges, the video can be pumped at 2 bits per unit time from this point to this point, 1 bit through each of these paths. But now suppose that there are 2 recipients of the video stream. Well, 1 bit is being sent this way, 1 bit is being sent this way, but there's contention on this link. So you can't directly stream 2 bits per unit time through this network to both receivers. Instead, we require the network itself to do a tiny bit of computation. So at this point in the network, the 2 bits of the stream are added together using the addition rule for GF2. Now at this point, this recipient gets the bit B1 and the bit B1 plus B2. This recipient can obtain B2 by subtracting B1 from the sum. This recipient gets the bit B2 and the bit B1 plus B2. So can obtain the bit B1 by subtracting. So you see, in this case, you can effectively double the throughput from this source to these two recipients using GF2 addition.